Hello there, friends and neighbors. I want to show you now how to use the normal probability distribution to approximate the binomial, which you can do under certain circumstances. Specifically, you can do it when NP and NQ are both large, where Q is defined by N 1 minus P. So let's just dig in. A drug test is accurate 95% of the time. The test is given to 205 people who have not taken drugs. What's the probability of exactly 196 testing negative? That is 196 successes out of 205 trials, with P, probability of success for any one trial, is 0.95. This is a binomial process. So I'm going to use the normal to approximate the binomial using the continuity correction. That's the first thing I'm going to do. The first thing I'm going to do is write down the information I've been given. I'm going to start by deleting the information I had from the previous exercise. Okay. So first off, I'm given P, which is 0.95. Oops, 0.95. I'm given N, which is 205. I'm given X, 196 successes. Okay. So in order to use the normal to approximate the binomial, I'm going to need to use the continuity correction. That means 196 is not good enough, because the probability of exactly 196 with any continuous probability distribution is always going to be 0 by definition. Continuous probability distributions have no area for any specific single value, so it's always 0. So what I'm going to do is instead define 196 minus 0.5 as the lower limit, 195.5, to 196 plus 0.5 as the upper limit, 196.5, 196.5. So all this area between these two numbers is what we're going to define as the value 196. Now the mean for our normal approximation to the binomial is going to have to be equal to n times p. That's the mean that we would have for the binomial itself. So that's what we're going to use as mu in our normal approximation, n times p. And then while we're at it, the standard deviation is equal to square root n times p times q. N times p times, well, rather than having q, I'm going to open paren 1 minus p. It's 0.05. Close it off, hit enter. So I'll put this here for reference. Square root n times p times q. Well, let's say 1 minus p. Okay. So that is what we're dealing with. Now, as I said, this is all valid if and only if NP and NQ are both quote-unquote large. Rule of thumb that I use for large is 5. Different books will use different rules of thumb. Maybe sometimes you'll see 10. Sometimes maybe you'll even see 15. Now let's check the assumptions here. Now we just did it for mu, so I know it's large, n times p. I'm going to do it again anyway. Here's NP. Here is n times q. And they're both large. They're both bigger than 10. So no matter what rule of thumb you're using, this is good enough. So what that tells me is that I can use the normal to approximate the binomial. It will look pretty good. I'm going to check it and confirm that now. Now again, the normal distribution is continuous. And so it is not exact, and it is in fact impossible to meaningfully compute the probability of one exact value. It's always 0, but this is going to be pretty close, I think, and it should, because I satisfied the assumptions. I'm going to sketch myself a normal curve. It does not have to be a work of art. It does not have to look good. It's just an approximation, just something for me to keep a handle on what I'm doing. So here I've got mu, which is, what was it? 194.75, and somewhere over here I've got sigma. Population standard deviation is 3.12, and what I'm going to do now is draw lines for my two x's. Let's see, what are they? 195.5 is bigger than mu, so they're both bigger than mu. Here's my x1, here's my x2. And it does not have to be to scale or work of art. It's just something that I can wrap my head around. X1 equals, what is it? 195.5, and x2 equals 196.5, and that's what we've got. I'm going to shade in the area in between. I'll shade it in red, and I'm looking for the red area. But norm dist is going to give me only left tail probabilities. By definition, that's what it can give me. So I can only do this by taking the blue area, which is blue area equals norm dist for x1 mu sigma 1. Those are the arguments you give it. And that's the blue area. The blue plus red, red plus blue, that's the norm dist for x2, the higher value. Let's make it purple. That'd be kind of fun. Norm dist x2 mu sigma 1. And that's what that is. And so what I actually need to do is get red equals red plus blue minus blue. That's what it is. Basically, I'm going to do this by subtraction. I can get the red plus blue with norm dist x2, and I can get the blue, and then I have to subtract. That's how we do it. Okay, and I'll just make that purple. So the p-value for the probability of observing a value less than or equal to x1 is going to be taken here with the lower x, so equals norm dist x1 mu sigma 1 and equals norm dist x2, the upper one, and mu sigma 1. So I get 0.713 and 0.595. Okay, those are the upper and lower limits. So to get the area in between, I do subtraction, the big one minus the little one, 0.11757. That's my answer there. That's the red area. The exact binomial value is a lot easier to compute, frankly. So we do that equals binom dist, and you plug in x and p, and then the last argument is 0 if you want exact, which is what we want, or it would be 1 if we wanted cumulative. And I'm going to say enter, and that is 0.124. So our question is 0.12, pretty close to 0.12. So 0.118, pretty close to 0.124. Well, yes. Yeah, those are similar. Really close together. So I'm going to label them. Enter the values into the assignment. I'm going to say, yes, they're close together. It looks pretty good. And I submit. And I get all greens. And everybody wins. That's how you do it.